Hello, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry, or the CMCC. The goal of our seminar series is to bring the scientific community together. Our seminars stream live on the third Thursday of every month at 10 a.m. Central Time and are available to watch anytime on YouTube. Our YouTube channel is home to all of our previous seminars, and we hope that you will take a look. Also, we are looking forward to an excellent group of speakers upcoming in the next few months, and we hope that you will join us for all of them. Before we get started, a great big thanks to a few people. First, Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, and two CMCC students who contribute significantly to the seminar series, Quintarius Moore and Katie Floyd. Thank you so much for joining us. Please do subscribe and follow us on YouTube channel, CMCC Mechanochemistry Discussions, and also follow us on Twitter. Quick notes that this webinar is being recorded. If you have questions for the speaker during the presentation, you can either email them to us at cmccdiscussions@gmail.com, and we can migrate them to the speaker for discussion at the end, or you can post them directly into the YouTube channel. Lastly, we're very pleased today to have today's speaker, Dr. Vladimir Šepelàk. Dr. Šepelàk obtained his diploma in solid-state physics from the Šepelàk University in Slovakia and his PhD in solid-state chemistry from the Russian Academy of Sciences. He did a postdoc at Braunschweig University of Technology in Germany, where he was later a leading researcher and professor. Since 2009, he's been a leading researcher and principal investigator at Karlsruhe Institute of Technology, also in Germany. Dr. Šepelàk is an academician of the Learned Society of Slovakia and president of IMA under IUPAC, as well as a member of multiple societies, networks, and editorial boards. His research interests include non-conventional synthesis of nanomaterials, mechanosynthesis, high-energy milling, mechanochemistry, and many more. It is indeed our pleasure today to have Dr. Vladimir Šepelàk for the mechanochemistry discussions.
Dear ladies and gentlemen, I am Vladimir Šepelàk. I am affiliated with Institute of Nanotechnology, Karlsruhe Institute of Technology in Germany. And first of all, I would like to thank Professor James Bates and Dr. Ashley Martini for inviting me to give you a lecture on structural disorder magnetism relationships in mechanochemically synthesized complex oxides. My presentation will deal with heterogeneous formation reactions, that means the synthesis of complex oxides, and you will see that we can start with various reactants and various numbers of reactant 2, 3, or even in many cases we observe formation of intermediates, and final our product is nanostructure complex oxide. Why mechanosynthesis? Why mechanochemical synthesis? There are many points to mention, but I would like to point only very relevant points which are dealing with mechanochemical synthesis of complex nano-oxides, and it is very simple one-step route to nanomaterials, and it is clearly visible on the first example, which presents the mechanosynthesis of 2,4-spinel iron germanate from 3 various adducts. You have hematite, you have metallic iron, you have germanium oxide, and as you see on the left-hand side, X-ray diffraction pattern clearly demonstrates that mechanochemical synthesis is completed in 2 hours, and product is a spinel containing ferrous cations, and you can see all the broad lines which demonstrate or indicate nanoscale nature of this product. On the right hand side, you see progress of mechanosynthesis followed by iron 57 Mössbauer spectroscopy. And as you know, these methods see only iron containing compounds, that mean only hematite and metallic iron. And with prolongation of milling time, with increasing milling time, you see the disappearance of the trace of the sextets corresponding to these both adducts. And after 2 hours of milling, there is a spectrum typical for ferrous iron in iron germanate. In many cases, as I mentioned, this mechanochemical synthesis of complex oxides goes through formation of intermediates, as it is demonstrated for mechanochemical synthesis of double perovskite strontium iron molybdate. You see that we started now also from 3 reactants, but it is heterogeneous reaction involving oxygen from vial in the milling chamber. And you see X-ray diffraction patterns, Raman spectra and Mössbauer spectra showing disappearance of fingerprints of reactants and formation of double perovskite after 240 minutes. The second important point why mechanosynthesis of complex oxides that it produces highly non-equilibrium phases which are not accessible by conventional routes. This is also clearly demonstrated in this slide or on this page, where in situ high-resolution TEM observation of the structural relaxation of the near-surface layers of mechanosynthesized perovskite bismuth ferrite are presented. And you see that this is observation time, that even irradiation of surface of this mechanosynthesized perovskite with an electron, electrons leads to the transformation or to crystallization and relaxation of this structural state. Why mechanosynthesis? The third point which I would like to mention, that mechanochemical synthesis provides access to novel nanosite compounds of any structural type. It produces a large volume fraction of interfaces surfaces, as it is demonstrated here. We can obtain using this mechanochemical route novel nanosite compounds of any type of structural state, including fully nanocrystalline material, as well partly amorphous, we say sometimes interface control nanostructure, or fully amorphous glassy nanosolids, the called nanoglassy materials. I included here, because I cannot give to details, I mention only here 3 publications dealing with all this type of structural state. And the second last point which I would like to mention, that materials which are obtained by mechanochemical synthesis usually obtain enhanced functional properties, the main motivation of our study. Okay, so sometimes we also obtain downgraded functional properties. My presentation deals with the structural disorder magnetism relationship of in nanoscale mechanochemically prepared materials, and to find this relationship, we should characterize a non-equilibrium structure at local scale. We have to determine non-equilibrium ionic distribution. We have to define what is the geometry of the structural units, what is the spin configuration in internal interfaces or interfacial region, and external surfaces, near surface layers of mechanosynthesized nanoparticles. That means we are using mostly for this purposes spectroscopic methods like Mössbauer spectroscopy, nuclear magnetic resonance spectroscopy, Raman spectroscopy, X-ray photoelectron spectroscopy, which these methods complement in many phases, the results obtained by space-averaged methods like X-ray diffraction or neutron diffraction or other. My presentation will deal with complex oxides which contain in the structure more than one cation sublattice, such as spinels, olivines, nullides, perovskites, double perovskites, and hexaferides. These materials have been considered as a very convenient model system for investigation of mechanically induced processes in ionic solids because of their structural flexibility, providing a wide range of physical and chemical behavior. Let's start with zinc ferride, which is spinel and which is paramagnetic at room temperature, and we shown in this publication that nanocrystalline mechanochemically synthesized zinc ferride exhibit an enhanced magnetization of 30 mMu per gram at room temperature, and magnetic ordering temperature of the nanocrystalline material prepared by mechanochemical route is about 11 times higher than near temperature of the bulk zinc ferride, which is 10 Kelvin. This bulk material is always reference material, and we prepare it always using conventional ceramic high temperature synthesis methods. To elucidate such derivation or such nice properties of this material, we performed surface studies of nanoparticles of zinc ferride using X-ray photoelectron spectroscopy. You see here bulk material, okay, is it crystalline size, 110 nanometers. We consider this material not more nanocrystalline. We say bulk material, and here is a material which is prepared by mechanosynthesis with a crystalline size of about 10 nanometers. You see the difference. Here, in this case, we have only one spectral component corresponding to zinc in A tetrahedral sublattice of the material. Iron is sitting on octahedral sides. And you see in the case of nanomaterials prepared by mechanosynthesis, we have two components, spectral components, and which correspond to both zinc on tetra and zinc on octa sides. And from the intensity of these spectral lines, we can calculate so-called degree of inversion of the spinel structure. In this case, is 0.41 is the concentration of zinc occupying octahedral sides in spinel structures. That means it is very nice information that we have some distribution, non-equilibrium distribution of zinc cations from these experiments. To complement information, we have to look at iron, and in this case, Mössbauer spectroscopy is very powerful. And you see here, we have also two subspectra, two sextets corresponding to iron cations on tetrahedral blue lines and red and octahedral sides corresponding to here is corresponding red subspectrum. And enhancement, we see that we have very nice picture about both cation, zinc, and iron in the structure of this material. From the intensity, we can also calculate, and it is almost identical with the information obtained from XPS and Mössbauer spectroscopy. And the mean enhancement of both the magnetization and magnetic ordering temperature in this material can be attributed to the onset of iron on tetra, oxygen, iron on octa sides, exchange passes, and also exchange passes iron on B sides, oxygen, iron on B sides with deformed bond angles. That means now we have elucidated what is the origin of this enhancement. And if we look at the degree of inversion in this mechanosynthesized material, 0.41, it corresponds to degree of inversion of a bulk material prepared by conventionally, which is quenched from 1700 K. That means it indicates or show you how far from equilibrium mechanosynthesized zinc ferrite is. Second example is also on the characterization of mechanosynthesized nanospinels, which are in para and diamagnetic state, using spectroscopic methods. And one example on the zinc stannate. Here is mechanosynthesis followed by X-ray diffraction, and here is the same progress of mechanosynthesis followed by thin magic angle spinning nuclear magnetic resonance spectroscopy. You see that within 4 hours of high energy bore milling, we obtain zinc stannate, starting now from zinc oxide and tin dioxide. And here is a comparison of these diffraction patterns. Here is bulk material reference sample, and here is in red line is a mechanosynthesized material. The same for NMR spectrum, and you see that we have additional subspectrum here. If we compare these two spectra, I can show you it is here on this picture. That means we are comparing now NMR spectra of mechanosynthesized zinc stannate and conventionally prepared zinc stannate. You see this additional red subspectrum corresponds to deformed tin or 6 octahedra, and this blue subspectrum is associated with regular tin or 6 octahedra. That means we have additional deformation of the structural units in the structure of this mechanosynthesized material. And here is the same comparison for the Raman spectra. We see also here in the case of mechanosynthesized material additional spectral components which indicate the presence of tin or 4 tetrahedra. As we know, tin in the conventional prepared material occupy only octahedral sites. That means now this is indication that we have partly inverse spinel. Also, in the case of another diamagnetic compounds like aluminates, complex oxides aluminates, we use, in addition to X-ray diffraction, here is a mechanochemical synthesis of a zinc aluminate. Also very short reaction time, 2 hours milling time, and we see the mechanosynthesized zinc aluminate in comparison to the standard material prepared conventionally. And what we also very important information is coming from magic angle spinning aluminium 27 NMR spectroscopy. That means we observe two subspectra for mechanosynthesized zinc aluminates corresponding to aluminium on octahedral and tetrahedral sides, in contrast to one subspectrum corresponding aluminium in octasides for conventional prepared material. From the intensity of this subspectra, we can again calculate the degree of inversion, in this case 0.31, which is huge deviation from equilibrium state. Even if we look at the morphology of mechanosynthesized nanoparticles, in this case I gave only here zinc aluminate and lithium aluminate from experimentally determined degree of inversion using nuclear magnetic resonance spectroscopy. We can even calculate volume fraction and thickness of this interfacial region. If we consider that the core of mechanosynthesized material is like bulk material, and on the surface of these nanoparticles there are cations distributions or randomly distributed. That means we have statistical distribution. In the case of 1, 3 spinels, it is 5/6. In the case of 2, 4 spinel, it is 2/3. And then we see that volume fraction of interfacial region is huge in mechanosynthesized material, exceeding sometimes even 50%. And the thickness, if we know the size of nanoparticles, we can calculate the thickness, which is about 1 nanometer, typical for mechanosynthesized complex oxides. The second example, which I would like to show you, is a separation of surface effects from the bulk effect on the magnetism of nanomaterials, and it is done for mechanosynthesized magnesium ferrite. You see that we have enhancement of magnetization in the case of mechanosynthesized magnesium ferrite, in contrast in comparison to conventionally prepared bulk magnesium ferrite. And here is demonstrated that the mechanosynthesis of the magnesium ferrite proceeds through direct, there are no intermediate phases. We have reaction time 12 hours, and Mössbauer spectroscopy clearly indicates a disappearance of iron oxide, hematite. You see no traces of this compound in 12 hours milled material in mechanosynthesized magnesium ferrite. And then if we look at low temperature Mössbauer spectra taken at external magnetic field, now the iron cations in tetra position and octa positions, the subspectra are clearly resolved, and from the intensity of this tube subspectra we again calculate the degree of inversion, and for bulk material it is 0.9. It is a concentration of iron on tetrahedral sides, on magnesium on octahedral sides, we see 0.9. And from the ratio of the second to first line, we can even calculate degree of collinearity, so-called spin canting angle. And we see that in the case of conventionally prepared material, our spins are collinear, but anti-parallel oriented on A and B sides. If we look at Mössbauer spectrum of mechanosynthesized ferrite with a size of about 9 nanometers, its Mössbauer spectrum is fitted with the same subspectra in the case of bulk material, which correspond to the core of this nanoparticle, and the rest of the spectral intensity is fitted with 2 additional lines which correspond to tetrahedrali and octahedral coordinated iron cations in the surface shell or interfacial regions, or near sulfur layers of nanoparticles. And we can see from the intensity of these 2 additional lines that the shell is really structurally disordered. We have observed nearly random distribution of cations with degree of inversion close to 2/3, 0.69. And also from the intensity of this second to the first line, we calculated the spin canting angle, about 30 or 40 grades for tetrahedrali and octahedrali iron cations in the shell. Of course, from the intensity ratio of these 2 additional lines to the total spectral intensity, we can calculate the volume fraction of interfaces, about 50%, and knowing the size of nanoparticles, we can also calculate the thickness, about 0.9 nanometers, similar to previous cases. And if we know information from Mössbauer spectroscopy about the ionic configurations and the degree of inversion, and about spin configuration, about the degree of declination or deviation, spin canting angles, we can calculate on the basis of Neal theory of ferrimagnetism, magnetic moment for the core, simple calculations give us one Bohr magneton for the core of nanoparticles, and for the shell, if we take the values from Mössbauer spectroscopy, we obtain value 2 times higher. That means we have magnetically active surface shell in magnesium ferrite nanoparticles. I mean, we see that the enhancement which we observed using SQUID or magnetization measurements is attributed to the effect of cation distribution, which causes increase of the magnetization, and spin canting tends to reduce, and these 2 effects are always competitive, and in this case non-equilibrium cation distribution won. It was is the same, but this magnetically active surface shell in magnesium ferrite nanoparticles was also confirmed using neutron diffraction. I will not go to details. In the case of nanocrystalline nickel ferrite, which was prepared by mechanosynthesis, we observed reduced magnetization. That means in this case, spin canting was prevailing effect over the non-equilibrium cation distribution. And you see, if we heat this material, saturation magnetization increases, and after heating at this temperature, this magnetization is close to that of bulk material. Now, second type of complex oxide, olivine. That means we have also 2 sublattices, like in the case of spinels. But in spinels, I show you if the case is with ferric ions, and now we have magnetics containing ferrous ions, and we have 2 octahedrali non-equivalent sides in the structure, M1 and M2. And here is an example of mechanochemical synthesis of one of the very important olivine mineralogical named firelight with orthorhombic structure. This material is, as you know, very important rock forming silicate. It belongs to the most abundant phases of the Earth's crust and upper mantle. And this material can also be, the olivine firelight can be transformed to its cubic polymorph gamma, with a spinel structure about 4 gigapascal and 1000 centigrades. But I only mention here its mechanosynthesis followed by Mössbauer spectroscopy. Again, we started with 3 adducts, and internal redox reaction took place between iron 3+ in hematite and metallic iron with 0 valency. That means in the end we have iron in the divalent state, ferrous ions containing firelight, and you see the mechanosynthesis was also very quick. 4 hours was enough to obtain nanocrystalline olivine, and from Mössbauer spectra we can even determine various stages of this process, like mixing of precursors and at the atomic level. Then here is a nucleation of iron silicoid phase after half an hour, very quick. As you know, nature synthesizes this material very long times, many millions years, and we are able to do it in half an hour in our reactors. And you see progress of after 4 hours of milling, we have no traces of adducts, and the mechanosynthesis of olivine is complete. If we look at Mössbauer spectrum of this mechanochemically synthesized olivine and compare this spectrum to that of bulk material, we see 2 spectral components in the case of conventionally prepared matter corresponding to ferrous ions on M1 and M2 sublattices. And Mössbauer spectrum of mechanosynthesized material was fitted with 4 subspectra corresponding to 2 subspectra with the same parameters corresponding to the core of nanoparticles, and 2 additional subspectra corresponding to ferrous ion in the shell. And you see that about 40% of ferrous ions in the material is in the interfacial surface layers of mechanosynthesized nanoparticles. And if we measure nil temperature or susceptibility, depending on the temperature, we can see that nil temperature of mechanosynthesized material is 65 Kelvin. It's the same as for bulk material, but we see now very broad distribution of this nil temperature. Is not so obvious, it's not so evident peak like in the case of bulk material. I know that part of your center or part of your group are interested in mechanochemical synthesis of perovskite. You say it force-driven perovskite synthesis. Therefore, I selected also 2 cases. It is case of double perovskite and case of perovskite AbO3. That means you see the progress of mechanosynthesis of bismuth ferrite here, followed by Mössbauer spectroscopy. In 12 hours of high energy ball milling, we obtain Mössbauer spectrum corresponding to bismuth ferrite nanoparticles in super paramagnetic state, and also this black subspectrum corresponds to the same material in magnetically ordered state. We would like to mention that system is nanocrystalline with an average particle size of 20 nanometers, and the surface of these nanoparticles or near surface are amorphous, as I showed you in the beginning of my presentation, that the surface is very reactive and reacts on the electron irradiation. That means this is this case. And we see very broad spectral lines which indicates a broad distribution of magnetic field acting at iron nuclei, and this reflects the presence of strongly distorted octahedra around the ferric ions. This distorted octahedra leads, of course, to the content spin arrangement. That we do not have some collinearity of arrangements, but we have some declination or deviation from this state. And if we measure magnetization of this material, mechanosynthesized bismuth ferrite, we see that it is enhanced magnetization in comparison to conventional prepared materials. And on the basis of Mössbauer spectroscopy investigation, we can say that this enhancement is attributed to the Kentid antiferromagnetism and due to the presence of distorted octahedra. The effect of Kentid spins manifests itself by the uncompensated magnetic moments of iron 3+ ions, enhancing the contribution to the materials of our magnetization. And second example also deals with bismuth ferrite, but with mechanosynthesized bismuth ferrite followed by thermal treatment. That means we have now nano bismuth ferrite nanoparticles with average size not 20 nanometers, but almost 100 nanometers. And it was interesting to observe one sextet, which is not typical for bismuth ferrite, because if we look at the bulk material, we have 2 components in the spectra corresponding to anti-parallel orientation of spins, which can be which corresponds to typical cycloidal spin arrangement. And we see that we were able suppress the cycloidal spin arrangement in this material due to distortion of this iron 3 or 6 octahedra. And it was also confirmed by X-ray diffraction, where we calculated not only in this case it was calculated tilting of 2 or 6 octahedra. So, I mean, we have here comparison of this bulk and mechanosynthesized followed by thermal treatment, and we see a long range distortion, and as I mentioned, deformation of iron 3 or 6 octahedra is a short range disorder characterized by Mössbauer spectroscopy. Now is the second perovskite, double perovskite. I will skip the explanation what is double perovskite, but you see that we have prepared this material mechanochemically, starting from 3 solid precursors, and also oxygen was involved in this synthesis. And as I mentioned in the beginning, this synthesis proceeds through the formation of intermediates, but finally we observe this material. Here is one again the information obtained from X-ray diffraction, Raman spectroscopy, and Mössbauer spectroscopy. That means if we look now at magnetization measurements, we see the blocking temperature and separation temperature 120 K, which correspond to the superparamagnetic state of mechanosynthesized nanomaterial. And we look at hysteresis loop. You see this room temperature hysteresis was analyzed in terms of superparamagnetic behavior using Bremner function, and the effective magnetic moment derived from the analysis attains a value of about 0.05. It's very small magnetic moment, effective magnetic moment, if we compare to the bulk material, which has a magnetic moment 4, Bohr magneton, and taking into account the formula which emphasizes the cation side occupancy and the spin alignment in the anti-side disorder strontium iron molybdate, the effective magnetic moment can be expressed using this formula. And from this, if we give here this value of magnetic moment to this relationship, we obtain the high degree of anti-side disorder, almost completely disorder, double perovskite with anti-side, degree of anti-side is about 0.5 is the maximum value. And it was also confirmed by Mössbauer spectroscopy at very low temperature, where we have only one component corresponding to this anti-side occupation of iron on anti-side sides. I think the most complex and most difficult case are complex oxides with many sublattices, as it is a case of hexaferrides. We have synthesized using mechanochemistry, and you see the bulk material, Mössbauer spectrum of barium hexaferride. We have the 6 subspectra corresponding to various coordination of iron in the structure. We have 2 octahedral sides, 1 tetrahedral Y, and 1 bipyramidal sublattice. And from the intensity of this subspectra, we can calculate the number of these ions per formula units in bulk material and in mechanosynthesized material too. And here is the only comparison of magnetization of mechanosynthesized material. This is the red hysteresis loop for nanoparticles with a size of about 40 nanometers. You see that we have very relatively small value of saturation magnetization, which can be which can be adjusted by thermal treatment, and we can receive particle size up to 220 nanometers, as demonstrated here. And it was observed that saturation magnetization of this hexaferrite decreases with decreasing particle size. And also the nano-size mechanosynthesized material exhibits enhanced magnetic hardness. That means coercive field of the nanomaterial is about 34% larger than that of the bulk material. And to explain such behavior, we have performed X-ray diffraction studies with and Mössbauer spectroscopic studies, and we see what is happening if we go to nano materials from bulk material. We see that the intensity changes ratio, and that means some of the cations from 12K octahedral sites goes to some interstitial sites. We say 12K star, and if we calculate the magnetic moment for such configuration obtained from Mössbauer spectroscopy, we see a real decrease of magnetization for nanocrystalline bismuth barium hexaferrite. And here is again the morphology of such mechanosynthesized nanomaterials, and we see that these surface layers or interfacial regions are disordered due to this shifting of iron cations from 12K sites to interstitial sites, which can lead to the dead layer, magnetically dead layer. That means with a layer with magnetization equals 0. And in this case, we can also, from magnetization data, calculate thickness of this surface shell, and it was a very good agreement with visual information from transmission electron microscopy, and from magnetization measurements we obtained the thickness of this surface shell of about 1.58 nanometers. That means it was, I think, this hexaferrite. And very shortly, I would like to mention that all these materials are highly metastable, and only 3-5 examples on the thermally induced disappearance of highly non-equilibrium cation distribution in mechanosynthesized, in this case, zinc gallate. You see gallium-71 magic angle spinning NMR spectra. For mechanosynthesized material, we observe again 2 subspectra corresponding to occupation of gallium on octa sides and tetra sides, and with increasing temperature of thermal treatment, we see a full relaxation or disappearance of this inversion to the state where gallium cations occupy only octahedral sides, and it is typical for conventionally prepared bulk zinc gallate with a degree of inversion 0, I mean normal spinel. This is the in situ observation of the relaxation of the locally deformed surroundings of iron ions in zinc ferrite. You see here a spectrum for bulk material and spectrum for mechanosynthesized material at variable temperatures. You see that with increasing temperature, wide distribution of electric field gradients at the iron nuclide disappear, and state after this temperature is comparable to that of bulk material. I already showed you that even irradiation of surface layers of mechanosynthesized material can induce relaxation or crystallization effect. That means transition to the more stable equilibrium state, and during heating of magnetically ordered nanoparticles, like in the case of nickel ferrite, we have a disappearance of superparamagnetism and the transformation to ferromagnetic state, as observed by Mössbauer spectroscopy in conjunction with transmission electron microscopy. You see growth of nanoparticles from nano to some larger size, and simultaneous disappearance of superparamagnetic state. And as you know, and as I mentioned to you already, that with increasing temperature of thermal treatment is the disappearance of this property, functional property, which was characterized by non-equilibrium structure. I will conclude my presentation with a few remarks. That mean non-conventional mechanochemical route to complex nano-oxides has been recognized as a powerful method for production of novel high-performance and low-cost nano-oxides, in this case magnetic materials. Nanocrystalline mechanochemically prepared oxides often possess a non-uniform structure consisting of the ordered nano-sized crystallites separated or surrounded by disordered interfacial surface regions, and we were able to determine volume fraction of these interfaces and thickness, and we observed a value of 60% for volume fraction of interfaces, and about maximum value was 2 nanometers for the thickness of interfacial region. And the main short-range structural feature of this disordered surface region in nano-oxides are non-equilibrium cation distribution, deformed polyhedron geometry. Okay, I did not show you probably the appearance of new nearest neighbor configuration in the surface shell of nanoparticles, and but also I show you appearance of non-collinear spin arrangement in the case of magnetic nano-oxides. Structural disorder in nano-oxides prepared by mechanochemistry is specially confined to their surface interfacial region, and nanocrystalline oxides exhibit unusual properties markedly different from those of their bulk counterparts, determined to a large extent by the structure of the interfaces surfaces. And mechanosynthesized oxides are far from equilibrium state, and their cation disorder is comparable to that of bulk samples at high temperature. I show you one example with the temperature 1700 K. My work is mainly supported by Deutsche Forschungsgemeinschaft within the priority program and present DFG project on nanoglassy oxides via mechanochemistry. Thank you very much for your attention.
Thank you so much for that presentation. We have a few questions from the audience. First, to what extent can the thickness of the disordered layer in the perovskite nanoparticles be controlled under ball milling?
I think that it is not possible to control it.
Okay.
We just time of reaction or mechanochemical synthesis is various in depending probably on the conditions of milling and probably on the material. You see here that here was, for example, double perovskite 240 minutes, and we stopped here because we do not see traces here of adducts. In this case, here is Mössbauer spectrum, that means hematite. But sometimes, as I show you, more than 10 hours of milling is needed. And what we see in some stationary state, that means if mechanosynthesis is already completed. Typical thickness of this surface shell is about 1 to 2 nanometers, but more 1 nanometers, but we cannot control it. I don't know, we do not work on such studies.
All right, thank you. Here's another question. It's clear that you can make many materials. I have one bulk question and one surface question. Do you know the oxygen vacancy concentration in the bismuth ferrite? And for any of these materials, can changing the conditions favor one surface facet over another?
Yeah, you are right that in many cases we also produce not only defects on the level of cations, like in the case of perovskites, anti-side disorder or but also we produce defects on the level of anionic sublattice and oxygen vacancies. I cannot give you exact value of delta, but I suppose that there is some concentration of vacancies on oxygen sublattices, but if we measure X-ray diffraction or some methods, it is always perovskite. I mean, it's not it is rather stable structure. We do not know the exact number of vacancies on oxygen sublattice.
All right, thank you. Another question. The magnetic properties of one of the oxides suggested an associated temperature of 1700 Kelvin. Does this represent an actual temperature reached during formation, i.e. hotspot theory, or just ion disorder?
Could you please repeat your question?
Sure. The magnetic properties of one of the oxides suggested an associated temperature of 1700 Kelvin. Does this temperature represent an actual temperature reached during formation or just ion disorder?
You mean relaxation of magnetic properties to the initial state?
Yeah. Give it a shot.
So that if we heat material, I'm not sure whether I answer your question, but magnetic properties of mechanosynthesized material are stable up to 600, 700 K. It is also information from not only from magnetization measurement, but also from spectroscopic methods. You see that spectra do not change from room temperature to, okay, here is not room temperature, but up to 600, 700 K, there is no huge change of local structure. That means not huge change corresponding to magnetic structure. Magnetization does not change, but if we heat material over 700 K, in this case, relaxation takes place. The anions goes to the initial position or to positions which are stable and with lower energy, and magnetic properties are going to direction of properties of bulk material, conventionally prepared. That means disappear, reduce magnetization or enhance magnetization, typical for nano state.
Do you have a plot that shows an extrapolation temperature of 1700 Kelvin? Does that sound familiar?
Yes, I can show you. You asked this one.
I think it was regarding that.
Yeah.
Slide.
Yeah, it is only imagination how far for equilibrium we are. Yeah, this is probably.
Yeah. This is it.
These are data. These squares are not our data. Are data for convention of mineral zinc ferrite. I think mineralogical name is franklinite, and O'Neill measured, I think, using neutron diffraction, temperature dependence of cation distribution in this material between tetra and octasides. And you see that with quenching temperature, it was efficient to quench material quenched this frozen degree of inversion up to 1200 K. And we extrapolated this data with a line, because it was only imagination how far we are now. And you'll see that our data obtained independently from various spectroscopic methods for this material. I presented you X-ray photoelectron spectroscopy and Mössbauer spectroscopy demonstrating degree of 0.41. I can show you here. Yeah, that means zinc on octasides concentration is 0.41, and we took this value and gave on the line and extrapolated that in our case is cation distribution correspond to quenching from 1700 K. I do not know whether I answered.
I think so. All right, yes. We're approaching our 1 hour limit, so I would like to thank you again for your presentation, and thanks everyone for attending today's mechanochemistry discussions.
Thank you very much. Have a nice day.
Thank you, Dr. Šepelàk, for that outstanding presentation, and thank you so much for joining us as part of the mechanochemistry discussions. Again, if you've missed any of our seminars, they are available on the YouTube channel, and I encourage you to go there and check them all out. In addition,